Welcome to Hot Chips 25. Session 2. Processors 1.
I'm Pradeep Dubey from Intel, Parallel Computing Lab to be more specific. This is our IBM session. It's really our big processor session. And the first talk is on IBM Powerade. And speaker is Jeff Stuecheli. Did I say it?
Stuecheli, sure.
He's an Austin man. Got his bachelor's, master's, PhD from UT Austin, and for last 18 years has been doing IBM Power. He's the chief Nest architect. I learned this recently. At Intel, we call them Encore, and this is, I think, a better sounding name, Nest architect. So he's the Nest architect. That means he worries about stuff around the CPU, and he's a master inventor, more than 90 patents filed, so definitely knows what he's doing. So with no further ado, Jeff.
Thanks. So yeah, I'm here today to talk about our Powerade processor, our next generation microprocessor for power systems. So here's a quick history of what the power processors were built over, say, the last 10 years or so. The goal here has been, server class, high performance, high core performance, large SMP scaling systems. And as you can see, we've kind of moved from, we've introduced multi-threading. We keep growing more threads each generation, more bandwidth each generation, larger caches as we go. So this talk today is about Powerade, which will be the next one on the chart. So what do we want to accomplish with Powerade? The first thing we needed was leadership performance. We wanted a Powerade processor to be, if you had an application that required extreme throughput, extreme single-thread performance, this would be the CPU that could deliver that. And so significant gains over prior generations in both thread performance and socket performance. And so that's what we're going for. And the reason we're doing this is really to enable, big data is something that's been pushed, is something that is driving the industry in many cases. And if you have big data, you need big performance to handle the data. We also want to make our system sort of self-learning, self-optimizing. And that I mean that if you load up, if you're consolidating, you're trying to get the most efficiency out of your system as you add, lots of partitions, lots of images that are concurrently sharing the device. And so we have a bunch of things that enable us to, this kind of system innovation where we can, monitor memory activity, make decisions on where memory placement should be made, and optimize code, basically be able to take a large SMP, which is what we're building here, many cores, and optimize that at runtime with hardware accelerators. And this is really to enhance our cloud efficiency, right? So these could be private or public clouds, but we want somebody who uses our systems to be able to get the most out of what they have. And beyond this, and this is recently announced, this is really a tie-in here to Open Power. I'm not sure if everybody saw this in the press, but Power traditionally has been only shipped inside of IBM systems, at least the IBM Power processor that we design. So what we're doing here is we think we have a great CPU and a great capability, and we'd like to partner with other companies and enable them to add their own IP and innovation to the system. And so you'll see things on here, this coherent accelerator processor interface, CAPI, that enables us, we'll talk about that in a little bit, but that enables other IP to be connected to the chip and sort of get into the guts of the system. We also have our memory interface is designed to be extensible towards emerging memory technologies. That's this agnostic memory interface. And our software stack, we're working on an open software stack that enables other people to do open source software build innovation around that. So here's our chip. It's always fun when you finally work on something for however many years, and you get to see, the processor hardware comes back. You get a guy to take a picture of it. So I got the picture, and I went home and talked to my daughter a little bit, and said, hey, she's 4. Your dad's been working on this for how long? What do you think? And she's like, well, I really like the pink, right? So I don't know if you can project it here, but she liked the color scheme. It's interesting, though. That's the vector scalar unit, which is a successor to VMX, which Pradeep, our session chair, actually designed the instruction set architecture for. So a little bit of a tie in there, but always fun to look at the thing after a while. So the chip itself here is 22 nanometer EDRAM. EDRAM is in deep trench capacitor, single transistor storage cell. 15 layers of metal, lots of wires to connect all this thing together with massive bandwidth. 650 square millimeters, so fairly large chip. 12 cores, 12 very powerful cores. We took our core from P7 and we beefed it up a lot. The next slide talks about that more in detail. But we have 12 of them on the chip. We also have accelerators. I'll go ahead and point. Those kind of live in this region here. So that's things that accelerate, like encryption and decryption, things like that. Transactional memory, I'm calling that an accelerator, but it's inside the core. So we support hardware managed transactional memory. We have some virtual memory assist accelerators, things to help out with moving data. One of our big value propositions for Power servers is we can take a partition that's running on an SMP and we can live migrate that to another system, and that enables people to balance loads inside of a cluster or upgrade, things like that. Got some accelerators there. Caches are fairly huge, I think is the best word for it. We have our 96, well, the System Z talk is next, and they have even larger caches than us, but other than the IBM Z talk, we have very large caches. So 96 megabytes of on-chip shared L3, which is pretty gigantic. The L2 caches are also quite large. One thing that we've added is a 128 megabyte off-chip L4 cache, which is something we used to have off-chip caches. We took those away in Power 7 Plus, but now we're adding back another off-chip cache in a very interesting way. It comes up a few slides in the future, but this is one of the very kind of cool things we did, I'd say, with the system. Memory bandwidth, we keep growing it by tremendous amounts. Thinking back to Power 6, we had about 30 gigabytes per second, which I thought was huge. And then 7, we made that 100, and now we have 230 gigabytes of sustained memory bandwidth, which is just we have these massively powerful cores. We need to build the infrastructure inside the chip such that you get the full use out of each of those, and that turns into an overall system efficiency and power efficiency. So we built in this massive memory subsystem. Overall bus interfaces, we've got our memory attached, we have our CAPI, PCIe infrastructure, we have a glueless SMP interconnect, and that's basically what we got. This is the only thing I have on energy management, so I'm going to spend a little time on it. I don't have a dedicated slide, but we have as many other people have talked about, if you want to do high-performance energy management, you need an on-chip microcontroller that sits there and monitors all the structures within the chip and can very quickly control voltages and control different characteristics of the machine. And so, to alluding to control voltages, each processor on the chip has its own independent voltage regulator that's integrated into the design itself. And so what we can do is we can monitor the exact workload on each chip with these critical path monitors. So they monitor what the exact voltage needs to be, and so then we can independently float the voltage of every core to be just high enough to accomplish what we're trying to do. And that saves significant energy. It also enables us, in some senses, to turbo at a higher level, and so you have a very interesting complex control loop that's maintaining power ceilings and getting the most performance possible out of a given amount of power to drive up your energy efficiency. So going forward, here's the core. Everything in the core is tremendously improved. We have a lot of double wide of buses. Caches are twice as big. The execution pipelines aren't, we don't have that many more execution pipes, but what we've done a lot of is grown the efficiency at which we can utilize those pipelines. And so you'll see down here at the bottom, we've got, compared to a Power 7 core, each core is twice as powerful as the previous core, which is a pretty huge gain. And so for a given core, you're able to do twice as much work. That's at a maximum SMT level when you're running SMT8 compared to SMT4 on a Power 7. But beyond that, if you just look at single thread performance, averaged across a broad range of commercial enterprise workloads, we have 1.6x performance at the single thread. And so that's accomplished through wider structures. There's a whole array of things we did to improve the core. So I think that's pretty impressive when you look at where other threads are going. We're growing our thread string pretty dramatically. Prefetch is better. We can all read this stuff. Let me keep going. So here's our big cache. We have in the middle here our 96 megabytes of L3 organized as a bunch of 8 megabyte banks. The way we run this is a Nuka cache. That's a UT Austin paper, so I like to reference them because I'm from UT Austin. But the idea here is why make everything uniformly slow with a shared cache? Let's take the data that's frequently accessed by one processor and move it directly next to that processor. And by doing so, we can build very low latency on average and very high bandwidth, scalable cache architectures. So we have our local fast slices. We have a massive chip interconnect to connect it all, combined with sort of privatized L2s. We have a bunch of policies here that involve, we replicate data if every processor wants it in the L2, but if data is less frequently used, then we form a single copy in the L3, and you're always trying to balance the, having everything at low latency and close, and also trying to garner a large amount of effective on-chip capacity to avoid going to memory. So that's kind of the balance we try and work with. Going forward a little bit, this is just a quick slide to show the massive amount of bandwidth we have. This is assuming 4 gigahertz. So 4 gigahertz isn't the only frequency we ship it at, but that's just sort of illustrating here. So if your processor was running at 4 gigahertz, you'd have 256 gigabytes per second of bandwidth from the L2 into the core. And these follow down all the way to memory, so you can bring in memory into a core at 128 gigabytes per second, which enables, that's part of what enables us to grow our single thread performance by such large amounts, is because if an application needs to consume memory, some sort of big data application, streaming data, we can feed the core very aggressively. But if you look at this, you can pull in terabytes per second into your core from your caches. So very impressive bandwidths on the chip. Going forward, the memory organization, this is something I spent a lot of time thinking about and working on with this, our memory buffer. So we typically always attach DRAM into our servers through a buffer chip. You just can't put enough memory on a direct attach approach. So like a typical processor might have 4 direct attach channels. We just can't get enough memory capacity, enough memory bandwidth out of standard DDR interfaces. And so what we do is we put DDR interfaces out on buffer chips that enables us to have more DDR channels, and then we run high-speed, low-power differential interfaces out to the buffer chips to feed things. So that's what we've always done. But here we've done some really cool things with the Centaur memory buffer, Centaur being the mythical creature, half horse, half man. So our buffer chip is half cache and half memory controller, which enables us to do some really interesting things, specifically drive huge bandwidth. So you got 8 of these Centaurs, each of their own high bandwidth interface. Each Centaur has 4 DDR channels, and so you've got 32 DDR channels of bandwidth, 410 gigabytes of peak bandwidth. And this is how we're able to achieve 230 gigabytes of sustained bandwidth. DRAM itself is hard to drive to high utilization without having some latency tails. There's a lot of things inside of the DRAM chip that haven't sped up in 15 years or however long. And so dealing with all these complex DRAM timing parameters, which keep getting worse as we go to DDR4 or even DDR3, you really need to keep DRAM utilization in check to have a decent latency profile. And so we have lots of DRAM bandwidth that we then can fully saturate our 230 gigabytes of on-chip bandwidth. Terabyte of memory per socket, so a reasonable amount of DRAM. Here's our buffer chip, and this is the interesting thing we went through. So we said we need 4 channels of DDR. We need that much bandwidth. But when you're building a buffer chip, you're worried about to keep the number of layers in the card reasonable. You really need all of your DDR interfaces to be on the peripheral of the chip. And so we put all our DDR interfaces on the peripheral of the chip. And then this is interesting. You see how small this is the driver and receiver for the thing that talks to the Powerade processor. And so that thing, when I say efficient, it's quite small, and it drives just as much. It's got a significant amount of bandwidth. So DDR interfaces are pretty big. DDR is a complex protocol. It's bidirectional, and so these drive quite a bit of area. So we ended up with a buffer chip where if we said, hey, we can build this in 22 nanometer EDRAM. If we do so, we've got this huge amount of logic area that we could put EDRAM in. EDRAM has very low leakage power, and so we can put 16 megabytes of EDRAM sort of in a donut hole, Beyond that, we can put the scheduler to talk to the DRAM, and so we have this sort of synergy DRAM chip that you think about direct attached memory having better latency than buffered memory, but with this solution we get better latency than direct attached memory because we hit the cache in some workloads 20–30% of the time, which wouldn't be that interesting if it was a processor cache, but if you think about it, every time you hit this cache you're saving power because you're not lighting up DRAM, and it works out to be, we have about 40 nanosecond latency to this thing, and so it drops the latency by a noticeable amount, but it drops the power by a more significant amount. And so I think it's very compelling from an engineering perspective to put something on a chip, to put eDRAM on a chip, and that lowers your overall system power consumption because you don't have to go to DRAM anymore. There's all kinds of things in here we did to manage the cache. I have a conference paper on this. You guys could look it up. But we utilize the cache as a write buffer such that we can sort of defer doing writes to memory when we have bursts of read operations, that we can do them in the future. So that helps out our latency characteristics. But there's all kinds of things we do here that are pretty impressive. One other thing I want to mention, and this is our DRAM, our buffer chip. I actually brought one. We'll flash over to it for a second. This is a smaller version of it for what it's worth. But these are our DIMMs. And so what you'll notice is we put the buffer chip on the DIMM. And so that does a lot of things from a RAS perspective that are very important. RAS, as far as reliability, we do high reliability servers. And so one of the issues you have if you're going to plug a terabyte of memory in per socket is if you do it with standard DRAM DIMMs, then this DRAM DIMM connector is one of the least reliable components in the computer. And so what you have is, if we were to do this, we'd have 4 DIMM connectors. If we were to put our buffer on the board, for example, we'd have 4 DIMM connectors, and those DIMM connectors would be running really not a very reliable DRAM protocol, right? Because bits can fail. I mean, there's some redundancy built in, but it's not a terribly reliable or correctable protocol. So by putting the buffer chip on the DRAM, we effectively cut our number of DIMM connectors by a factor of 8 because we can put multiple ranks all on one card. So we remove that failure point from our systems. Beyond that, the protocol we run across the DIMM connector is now a CRC replay protocol where we can handle bit failures in a much more elegant way than across a standard DDR interface. And so this enables us to have a much more reliable memory system that enables us to put this much memory behind a socket without having to go out and repair DIMMs every 3 months or whatever. So I think that's a pretty important thing to mention. So going forward, socket performance, so you got all these great cores. How much do you really get out of a system here? You get pretty massive speed-ups here. We're talking about over 2x performance over our just previous generation Powerade Plus system. 8-core system going to 12 cores. We're getting 2.5x the performance on some important commercial workloads. So this is I think very compelling and interesting as far as growing in just one process generation, going from 32 nanometer to 22 nanometer. We've got these very dramatic performance increases. So a couple other things to mention. We traditionally have, going back for generations, have built our own proprietary bus I/O protocols. So we had high bandwidth custom. But it's interesting that the industry with PCI Gen 3 is now better than our proprietary solution. So I think PCI 3 is a pretty interesting story. So we went with direct attached PCI Gen 3. We can build out wide I/O subsystems with PCI switches. We have virtualization and network adapters now, which reduces the need to have huge numbers of adapters. And so we're able to do this, and this gives us some latency advantages in some sort of high frequency trading type markets where latency is key. So we got direct attach PCIe. We also run our CAPI protocol across this PCIe protocol. I have one more slide on that in a little bit. We're not going to go into too much detail. A little bit isn't right now. Let's talk about it. We're going to share a lot more details on what this protocol is. This is just kind of a little bit of a teaser to get people interested in it. But basically, what we can do is today, if you want to attach an FPGA, for example, to a PCIe bus, you don't have, in many cases, pointers. You can't reference pointers very easily. I think there was maybe some discussion on this yesterday that might have been good for me to see. But you can't have hardware managed cache coherence, right? So if you're trying to move something to be accelerated out to an FPGA, it's a bit laborious to do DMA transfers to get everything out there. You have to potentially transfer large amounts of data. So what we've done here is we we put a unit on the chip called the cap unit, ending in a P. The P stands for proxy. And so what that does is it sort of, if you look at what a processor cache would be, we've split that cache controller with half of the cache controllers on the coherent bus and half the cache controllers over here on this power service layer. So we have this IP block we can deliver to an FPGA vendor such that somebody can put an accelerator here that just talks effective addresses, does loads and stores across this interface, and that becomes sort of proxied over here on the processor bus. One key reason we put a proxy here versus extending our coherent bus across here is if you look at, say, if you're going to attach an FPGA with just your standard processor SMP bus, you have to snoop all the traffic, right? And there's a heavy burden you place on the FPGA. With this, the only thing that goes across the link is just what needs to. You know, if the processor asks for a line that's modified on the FPGA, we'll send that request across explicitly. So this enables us to sort of isolate the FPGA from the rest of the system with this little proxy thing. So there'll be more stuff on that in the future, but I think it's interesting to talk about. So this is sort of the chip summary. As you can see, you know, we grew bandwidth. We've talked about all this. We've grown cores, bandwidth by fairly dramatic amounts, especially if you look at it from just a one process step generation from one to the next. Going forward, so power systems traditionally, our traditional markets have been banks, financial customers, large retail, and so we've got a large install base in the Unix space, but we think our systems are useful outside of that, and so we're working to expand our importance. And if you look at it, all those microarchitectural things that we have in there, with large caches, large bandwidth, lots of threads, lots of strong threads, those all kind of turn into what is required for sort of analytics, big data, right? So if you're doing big data, you're traversing graphs, you're analyzing large volumes of data. So all those features we built into our chip that work very well for our traditional customers are also very effective for emerging data analytics. And so we want to sort of accelerate that through our traditional customers here. These are a list of all the IBM-owned analytics companies, which kind of makes sense that if you want to optimize software, you partner or buy somebody. And then we have some real, the other thing that's interesting is, IBM Watson, the Jeopardy thing, which I think a lot of people might have seen on TV. I thought that was pretty cool to watch. It's the best Jeopardy episode I've seen. That was Power 7 based, right? And we're not, we're still going places with that Jeopardy technology. We're not just doing game shows, we're doing healthcare. And you can imagine that if you have 3x the performance of a Power 7, you can start to do very compelling things with healthcare. And this is actually one of the interesting things about IBM and being a very strong research arm, our own processor development. We have this huge vertically integrated stack to build really interesting, cure cancer type of solutions, which is why that's very exciting. We're doing that. Just to kind of harp on the analytics here for a little bit, if you're doing big data or big data analytics, cognitive computing, you need lots of capability, lots of throughput. In many cases, you also need to have strong single-thread performance. You've got this Amdahl's law thing, and we've seen this in several of the analytics packages. At some point, the serial part becomes very important and becomes dominant. And so having a strong thread is highly important towards a lot of analytics things. Beyond that, we have these CAPI accelerators, which enables us to sort of have a window into being able to do heterogeneous computing, be it with FPGAs or GPUs. And we also, think about all the synergy you have. If you can go and meet with the chief technical officer and speak openly with DB2 or NetEase or any of these software companies we've purchased, that enables us to sort of, lay all our cards on the table and come up with a really good solution, as opposed to if we were in separate companies, we'd have to sort of talk through NDAs. And, so we can do very efficient optimization of our entire stack across these broad range of companies that IBM has purchased over the last, say, 5 years. So this is, I think there's a lot of opportunity here and a lot more to come. The other thing, and this is kind of what I'm going to finish with, is Open Power. This was announced, I guess, about 2 weeks ago, where IBM has this great processor that we want to share and we want to innovate beyond our own ecosystem. And so we went out and we're effectively partnering with this list of companies you see on the list here to build systems based on Power 8, is really the flagship thing to start with, where we'll be able to use our leverage our high performance, high capability system, combine that with other people's area of expertise to make very, very impressive systems and really kind of grow our ecosystem and do things beyond what we've done. I'll come back to Watson here. Watson wasn't a traditional workplace, wasn't a traditional workload for us, right? That's a new thing out of research where we were able to do something very compelling and very amazing with power technology. We'd like to find more of those opportunities to come up with, and partnering with other people enables a larger ecosystem and more, people thinking about it and thinking about it their own ways, and that's how we're going to grow our power ecosystem, is what we're doing with that. So that's what I have. Hopefully I covered everything at a reasonable rate. Didn't go too fast, but thanks. Are there any questions?
Yeah, please identify yourself before you ask the question.
Great paper, great technology. This is Sam Nastiger from AMD. So you mentioned per core VRMs. Does that mean on-die magnetics, inductors, or are those linearly regulated?
You would have to ask the circuit person about that. So I'm the Nest guy, and then this is a core circuit technology. So, but we can get a follow-up with somebody who can speak to that more directly. It's on die, right? Regulation per core, but I don't know exactly how it works.
Okay.
But come and talk to me later if we want to try and work something out.
It's Ando from Micron. My question also regarding to the VRM, and as I understand that you don't know the details, but may I ask that what voltage does the chip supply?
Well, it's dependent on, we have per part voltage, right? So it's kind of.
No, I'm talking about the outside supply to the chip.
That's also variable based on the particular part you plug in. So, and not something we,
Bill Rash, Intel. A question I had, I guess, is in the core. I'm hoping you could talk about how many instructions do you decode per clock in order to feed the 8-wide dispatch?
Right. I believe we do 16. It works out to be a power of 2. Because that's the width is based around
So you think they decode 16 instructions?
Correct. I believe that's the right number.
Mm-hmm. Okay, thank you.
Yep.
All right, so this Ethan from Oracle. So you have shown the performance numbers, but what about the power numbers compared to the Power 7?
What's that?
I'm asking what's the power number compared to the Power 7?
It's effectively the same. We ship in a range of systems, and we're shipping in the same power form factor as the Power 7.
All right, thanks.
Krishnan from HP. When is this chip going to be available?
We're not announcing product availability at this talk.
Where are you? Are you free to say where you are in the cycle?
I have a part here. We have a lab full of systems.
Let's thank the speaker. Yes. Our next speaker is also from IBM, Robert Sonnelitter.
Yeah.
He's been with IBM now many years, advisory engineer at IBM, graduated from CMU, and has been on 5 generations of System Z machines. And he 16 US patents, and he's currently leading a multi-chip coherency protocol team at IBM for the future Z system. So let's welcome Robert.
Thank you. Thank you. Is this on? Right. Thank you very much, and good afternoon, everyone. I'm really excited to be here today to talk with you about the processor subsystem of the latest generation of the IBM Z Enterprise class system, the Z EC12. As Jeff just alluded to, I think you'll find this presentation to be very rich in cash. Thanks. But first, though, I have a question for everybody in the audience. Can I see a show of hands for anyone here who's used a mainframe recently? Wow, actually a couple, really good. A few hands, but not too many. So let me take a moment then and ask the same question in a different way. Can I see a show of hands for everyone who's used a credit card recently, or an ATM machine, or gone to the grocery store and found the shelves stocked with your favorite brands of coffee or ice cream? So that's excellent. I knew that I would find a lot of mainframe users here, because even if you don't realize it, if you've done any of those things or dozens other like them, odds are that there's a mainframe behind it. The handling of all your transactions and many billions of others requires a machine that is scalable, robust, and reliable. And today, I'm going to cover how the design of the Z-EC12 cache hierarchy enables it to meet those requirements. So those of you who were here last year for HotChips24 had the opportunity to hear my colleague, Kevin Shum, introduce the processor core of the Z-EC12. And it's a pretty amazing core, the fastest in the industry, running at 5.5 gigahertz, and with many cool new features like the transactional execution facility. But the processor core is just one piece of the overall system. So today, I'd like to take the opportunity to dive a little deeper into the Z-EC12 and share with you some of the innovative features and design challenges that comprise its cache hierarchy. So we'll start off with a short history lesson, so you can learn about the evolution of the shared cache design in System Z, how it gets used in customer environments, and how that factors into its design. We'll follow that with an overview of the on-chip shared L3 cache and learn about its features and design challenges. Next, we'll take a look at the off-chip shared L4 cache and the coherency protocols that allow us to build a large, scalable SMP system. And last, but certainly not least, since this is a System Z machine, we'll take a look at some of the reliability, availability, and serviceability features that are baked into the design. Since this is the first time that we've talked about the System Z cache hierarchy in a forum like this, I think it'd be useful for me to start with a brief history of the shared cache design in System Z. The Z-EC12 is the latest in a long line of System Z machines stretching back to the early 1990s that feature multi-level processor caches with at least one large shared cache level. As we've grown the total cache size and system capacity with each generation, the structure and content of the cache hierarchy has evolved to meet the changing needs of our customers. The highlights of this evolution are changes in the number of cache levels, changes in the SMP interconnect topology, and changes in the cache memory technology. From the two-level cache hierarchy of the last bipolar mainframes, we added a third level of hierarchy on the Z10 machine and introduced a fourth level of hierarchy on the Z196 in 2010. During that time, the SMP interconnect topology has evolved from a single multi-chip module node to a system with 2 nodes on the G5 machine, then 4 nodes connected on a ring on the Z990, and finally, the current structure with 4 nodes fully connected together introduced on the Z10. Lastly, starting on the Z196, we migrated from SRAM to EDRAM for the last 2 shared cache levels to reap the density and power benefits that come with using DRAM. One of the things that makes System Z unique from other machines on the market is the manner in which it's used. This is a machine that is designed with the demands of the enterprise computing environment in mind. So what are some of the important characteristics of this environment? Well, one of the most important things is that it's a highly virtualized environment with the potential for hundreds or even thousands of virtual machines to be running on a single system. This leads to a system environment with many diverse, heterogeneous workloads running simultaneously on a single machine. And as a result, the system resources like the processor, memory, and I/O are both highly utilized and heavily shared. This is also an environment with a high degree of data sharing between the cores, and one that requires a responsive system with guaranteed processing times for I/O transactions. So that was an overview of the environment in which System Z operates. Now let's talk a little bit about how this gets translated into the design. The main course is through the use of customer representative workloads to model and measure how well the system performs under various conditions. Our target for each generation is to provide guaranteed hardware-based performance improvements, and for that measurement we use our large systems performance reference, which is a suite of benchmarks designed to represent typical customer workloads. We have 3 flavors of the LSPR that we look at called high-D, mid-D, and low-D, with the high, medium, and low referring to the intensity of the workload mix with regards to the memory subsystem. As you can see from the graphs, with each generation, we've provided consistent performance and system capacity improvements, which enables our customers to do accurate capacity plannings for new systems. The LSPR is not the only benchmark we refer to during our development, though. We also refer to external benchmarks and custom stressors to ensure that the design smoothly handles corner cases and newer workloads. The result of modeling these workloads has helped uncover several important features necessary to meet our customers' requirements. Most important to this talk is the structure of the cache hierarchy that resulted, with private L1 and L2 caches that provide low latency access to data. These private core caches are backed by multiple levels of large shared system caches, which, as you can see from the graph, are critical to minimizing our overall CPI by reducing the number of requests that go to memory. Having multiple levels of large shared system caches also allows us to maximize the affinity of cache data among groups of processors and add additional processors to the system in a manner that ensures our SMP latency is relatively flat as the system scales upward. All right, so now that you have an understanding of some of the factors that are important and influence our system design, now we can get into the really good stuff. This diagram is a logical representation of the cache hierarchy of a single multi-chip module node on the ZEC12. As you can see, we have a 4-level cache hierarchy. The node has a large EDRAM L4 that is shared by up to 36 processor cores. These 36 processor cores are divided into 6 groups of 6 cores, with each group of 6 sharing a large EDRAM L3. The L1 and L2 caches in our design are private to each core and are private split caches. The L1 and L2 cache levels are right through, while the L3 and L4 cache levels are right back, and all cache levels are inclusive. The ZEC12 isn't limited to a single node, though. As you can see here, it can contain up to 4 nodes, which are connected together with a fully connected topology at the L4 level. Each L4 in the system operates as a peer to the others, so in a fully configured system, we can have 1.5 gigabytes of L4 cache. So that was a logical overview of the design. Now let's explore the physical side of it. A few slides ago, when I discussed the logical partitioning of the caches on the node, and as you might have guessed, that maps pretty directly to the physical arrangement. Our design consists of 2 distinct chips, which we refer to as CP and SC, and we package them together, and we package 8 chips together on an MCM with 6 CPs and 2 SCs. Using the multi-chip module allows us to optimize the latency between the chips as we're able to tightly couple them. Each MCM also contains the interfaces to 3 memory controllers, 8 GX Plus I/O interfaces, and 3 SMP fabric interfaces to the other nodes in the system. So let's start taking a look at these chips in a little more detail. Here's a picture of the CP chip floor plan, and it's a pretty amazing chip, as you can see from all the facts listed on the side. What's most impressive to me is the content and frequency of this chip, with 6 cores running at a constant 5.5 gigahertz and a 48 megabyte shared EDRAM L3. Since the focus of this chip is the L3 cache, I've highlighted it for you in blue in the middle of the floor plan. Physically, the L3 is divided into 3 distinct units: L3B, L3C, and L3Q. The L3C is located in the middle of the chip and serves as the brains of the L3. On either side, it is flanked by the L3B and L3Q data flow complex. The L3Q represents the cache EDRAM macros themselves, and these are arranged in a ring around the L3B, which is our gigantic cross-point data switch, used to simultaneously buffer and move data between the L3 cache and all the other units that the L3 interacts with. In total, each L3 is a 48 megabyte shared cache, but we've divided it into 2 identical 24 megabyte slices based on a low order address bit and creatively named L30 and L31 to enable greater concurrency. The slices operate independently of each other, and each slice has connections to all 6 cores on the chip, as well as the memory controller, the I/O interface controller, and the L4 cache. The L3 also includes a number of beneficial performance features. Since the cache is shared between processors and I/O, this allows us to do I/O partial line operations in the L3 and see a latency benefit for accessing these shared lines. We also include hardware accelerators to improve the performance of page-based operations, and a pretty cool store history table that we use for preemptively returning exclusive access to conditionally exclusive fetch requests. Each L3 slice is organized around its central pipeline, which, in addition to providing serialized access to the L3 directory and cache data, serves as the point of coherence in the L3 and is used to arbitrate for all shared resources and interfaces. For an L2 fetch miss that hits in the L3, the pipeline is broken up into 7 cycles. During the first pipeline cycle, which we call C0, we do a priority selection among the available operations, including new L2 misses being sent to the L3. In the C1 cycle, we do a lookup in the directory to determine the hit state and which set the data resides in. In the C2 cycle, we start a speculative access of the EDRAM and distribute the directory hit results to the state machines and cache controllers. The C3 cycle is when the fate of the pipe pass is determined. If all the necessary resources are available, then the operation proceeds onward, and we begin accessing the data in the C4 cycle, where we do an ECC check and correct before returning it to the core 2 cycles later. If there is a conflict with another core attached to this L3, or the line misses the L3, the C4 cycle is also when we send the coherency messages to the L2 or L4 cache levels. The other main operation that the L3 does is a store from the core, which has 2 important differences from fetches. One difference is that due to our strongly ordered memory model, processor stores are required to hit exclusive in the core, exclusive in the L3 owned by the storing core. The second difference is in the L3 pipeline, where, as you can see, the EDRAM access occurs later because we need to move the data from the L3B to the correct EDRAM based on the lookup results. Our biggest challenge in the L3 design was finding the right balance between fetches and stores. As the first level write-back cache in the system, with 6 busy cores doing a large number of small random stores, it's necessary for the L3 to support a high store bandwidth in order to avoid stalling the cores. But this store pattern can also significantly affect the availability of the cache for fetches and cause them to encounter long queuing delays, which would increase the access latency to the L3. The interaction between fetches and stores is complicated by the usage of EDRAM with its multi-cycle busy and access times, which require complex cache access scheduling. The first important step we took to dealing with this challenge is in our partitioning of cache lines across EDRAMs. We divided each slice into 2 independent banks, and within each bank have a 4-way interleave to spread the cache lines across multiple EDRAMs. This partitioning has benefits for both fetches and stores. For fetches, it allows us to match the busy time of the EDRAM with the busy time of the data bus, which reduces resource conflicts. For stores, interleaving the line allows us to busy fewer EDRAMs for each store, since each store ends up using only 1 interleave, and thus allows us to have fetches and stores operate to the same bank concurrently. Managing the EDRAM is handled by our cache interleave scheduler, which is responsible for keeping track of all active fetches and store operations to the cache and ensuring there are no collisions at the EDRAM. To start a fetch operation, the interleave scheduler needs to reserve all the interleaves necessary to ensure that a fetch is able to continuously access a cache line. Stores, meanwhile, only busy a single interleave. So while that simplifies one aspect of the cache scheduler, the fact that fetches and stores start at different pipeline cycles adds both complexity and significant blocking of the interleaves for the stores. To illustrate this problem, let's take a look at the graphs here. At the top graph, which is showing an example of fetch versus store conflict for a store that's targeting interleave 2 with the fetch followed by interleave 1. The store is the first operation in the pipe, and it busies the EDRAMs for the cycles in purple. But in order to reserve the EDRAM for those cycles, we need to ensure that no fetches start accessing any interleave in the cycles highlighted in yellow. So the fetch, which is immediately following the store in the pipeline, gets stalled because of the resource conflict, and as a result, must wait for the conflict to clear, at which point it then accesses the cache in the green cycles. To address this issue on the ZEC12, we added what we call store platform registers that allow us more flexibility to schedule the store by holding the data closer to the EDRAM and allowing the actual commit to the EDRAM to occur when it's convenient to do so. This allows us to maintain our store throughput, but minimize the interleave blocking because it makes the actual EDRAM write of the store asynchronous to the L3 pipeline. The result is shown in the bottom chart, whereas you can see the green cycles moved 5 cycles sooner, and the store commit was only slightly delayed. While managing the EDRAM was our biggest challenge in the L3 design, it was not the only obstacle we faced. Another significant challenge was integrating the data flow due to the intersection of the increased cache size, increased core count, and the desire for a symmetric MP design. In comparison to its predecessor design, we doubled the L3 cache size and increased the number of cores by 50%. This results in the furthest core being relatively further away, and also substantial growth in the number of concurrent operations that we need to handle. Our solution here focused on the data flow through the L3B. By creating a balanced design where the bandwidth to and from the cache closely matched the needs of the attached cores and I/O, we were able to minimize the wiring resources needed to get to and from the EDRAM. This helped us make intelligent use of the 15 metal layers in IBM's 32 nanometer process and dedicate the fast high-level metal to ensuring that the cores have uniform low latency access to both L3 slices. The second chip used in our cache hierarchy is the SC chip. This is a pretty amazing chip in its own right. What I think is most impressive is the sheer size of it. Each SC chip has 192 megabytes of L4 cache and contains over 3.3 billion transistors. The physical partitioning of the L4 is much like the L3, with the L4C, L4B, and L4Q units serving roles similar to their L3 counterparts, but beefed up for the increased L4 capacity. The L4C is in the center of the chip, and it's surrounded by the L4 cache directories. These are flanked on either side by the L4B cross-point switch, and all of this is surrounded by the over 1,000 EDRAM macros that comprise the L4 cache. Each node contains 2 SC chips. The address slicing that we saw at the L3 level is handled by the separate chips at the L4 level, with the 2 SC chips operating independently of each other. Each SC is connected to all 66 CPs on the node and contains the SMP fabric interfaces to the 3 other nodes in the system. The L4 is the coherency manager in the system. It controls all accesses to memory, and all cache ownership state changes must be consistent with the L4's view of the system. So, for example, the L3 can't upgrade its state to exclusive without permission from the L4, nor can it access memory without direction from the L4. Like the L4 cache is organized around its central pipeline, but the larger size of the cache and chip necessitate a deeper pipeline to cover the more than 20 millimeters of distance to cross the SC chip. So where the L3 started its EDRAM access in its C2 cycle, the L4 EDRAM access starts a cycle later. And there's an additional cycle of reach on the output of the EDRAM that makes the data return to the L3 occur in the C8 cycle. Despite the longer pipeline depth for accessing data, the L4 still maintains a tight recycle loop for dealing with cases of address or resource conflicts. The large size and scope of the L4 cache provided a number of challenges during its design, the most interesting of which is managing the large number of concurrent operations and shared resources, such as buffers, buses, and memory. In many ways, the L4 functions like a network chip, ensuring quality of service and fairness for different classes of operations, like core fetches, I/O requests, or hardware accelerator operations. The centralized ordering and fairness logic in the L4 allows us to build dynamic queues for requests for shared resources and balance access to those resources based on the needs of these different request classes. In doing so, the L4 is able to guarantee responsiveness to all classes of operations. Our on-node cache management is derived from the MESI protocol, with the L4 cache serving as the backing storage for the peer L3s. All communication on the node between the L3 chips is routed through the L4. So on L3 to L3 interventions, the L4 steers the requests to the appropriate L3s. When an L3 miss arrives at the L4, it snoops the L4 directory to determine the state of the line on the node. Lines that are shared by multiple L3s are always sourced from the L4 cache copy and follow the flow of the green arrow. For the case where an L3 is seeking exclusive access to a shared line, the other L3s guarantee the time to deliver the invalidation message to their attached L2s in order that we can deliver the response faster to the requesting core. L3 requests that need to access data that's owned exclusive by another L3 follow the flow of the orange arrow, and data from the source L3 is routed back to the requester via the L4. Between the peer L4 nodes, we implement an enhanced MOSI protocol. Using bits in the L4 directory, we call IM and MC to differentiate between the states. Other important identifiers in our protocol are MM, which is the node the memory is attached to, and ghost, which is a flavor of invalid created by exclusive interventions that indicates the data likely exists IM on another node in the system. If there's data exists IM in any state, in any L4 cache, that cache is the point of coherency in the system, and that L4 will service any data requests. If there's no IM node in the system, then the MM node is the point of coherency, and data will be sourced from the memory. So following an example fetch request in the diagrams on the side, we start with a request from node 0 that wants exclusive access to a line. In the top diagram, you can see it gets broadcast to the 3 other nodes in the system, where it snoops the L4 directory. Each node then broadcasts the results of the snoop to the other 3 in a coherency message we call a partial response, as you can see in the middle diagram. All nodes will see the broadcast or partial response from the other 3, and along with their local state, can combine these results together to determine what to do without any further intervention from the requesting node. In this example, node 3's partial response indicated that it has an IM copy of the data. The other nodes will see that and know that node 3 will provide the data to node 0, as you can see in the bottom diagram. The final major influence on our cache hierarchy design is the System Z commitment to reliability, availability, and serviceability. Our primary focus in the hardware design is to protect the integrity of customer data by maximizing system reliability. From the beginning, we architect into the design the ability to detect and recover from a large variety of errors. The RAS features of each level of the cache hierarchy are tied together to maximize our overall system reliability. It starts with our private write-through core caches that enable us to tolerate any core fault via transparent processor recovery actions, and is followed by our unique array failure detection and isolation algorithms that enhance the resiliency of the shared system cache levels. This is backed by our memory RAIM interface that brings the benefits of RAID 5 protection to memory DIMMs. Finally, our concurrent maintenance function allows the hardware to be upgraded or repaired without disrupting customer workloads. Well, I hope that you've enjoyed this look at the ZEC12 processor subsystem and now have a better understanding of its architecture. We've touched on many of the design challenges faced during the development of both the L3 and L4 cache levels and some of the innovative features that resulted. These features include how the structure of the L3 enables it to balance the high bandwidth demands of fetches and stores, how the L4 manages fairness among its many concurrent operations, and how both levels work together to maximize our system reliability. The robust capacity and tight coupling of the L3 and L4 cache levels provide for smooth SMP scaling in a heterogeneous virtualized working environment. This allows the ZEC12 to take on many new workloads and support the evolving needs of the enterprise computing environment. So, thank you, sir.
Questions?
All right, I get off easy.
No? No questions?
funny shaped sculpture, whether that actually serves any purpose other than marketing?
Which pack?
The overall cabinet.
That's a good response. I like that. The stealth radar capabilities.
Can you just identify yourself, please?
You talk about the processor running at 5.5 gigahertz. You talk about the memory, the cache subsystem, and the clock pipeline through there. Is that at that speed or the lower speed?
It's at a lower speed. Both the L3 and L4 cache operate at a 4-to-1 ratio with the core.
Okay.
All right.
Thank the speaker. I guess time for our keynote.